Hello, this Recitation 9 video will cover normal distribution, uniform distribution, and exponential distribution. Miraculin, a protein naturally produced in a rare tropical fruit, has the potential to be an alternative low-calorie sweetener in plant science. May 2010. A group of Japanese environmental scientists investigated the ability of a hybrid tomato plant to produce miraculin. For a particular generation of the tomato plant, the amount X of miraculin produced, measured in micrograms per gram of fresh weight, had a mean of 105.3 and standard deviation of 8. Assume that X is normally distributed. So we want to find the probability that X is greater than 120, find the probability that probability of X in between 100 and 110, and find the value alpha for which the probability of X is less than alpha, which equals 0.25. So first, let's find the probability that X is greater than 120. So the key information to take away from this prompt is that we have a normally distributed variable X. The mean is 105.3 and the standard deviation is 8. So first, to find the probability that X is greater than 120, there's two ways to do this. So first, you can compute a z-score for it, and a z-score takes the normally distributed variable and standardizes it by subtracting the mean and dividing by the standard deviation. And a standard normal distribution has a mean 0 and standard deviation of 1. So I'm going to show you two ways to do this. So the first way is to compute the z-score, and I'm going to zoom in so we can see a little more clearly. And there's 3 steps. So first, to compute the z-score, you're going to take X minus mu over the standard deviation, and here X is where X is going to be 120 minus 105.3 divided by 8, and that's 1.8375. And then, so essentially the probability of X greater than 20 is equivalent to the probability of Z, and Z is the standard normal variable greater than 1.8375. And then you can use a table and do 1 minus the value. And so a table will look like this. And so the table values represent the area under the curve, but to the left of the z-score. So here, if we go back to that slide, so we're interested in the probability of z greater than 1.8375. So we would do 1 minus that value to get the probability. We would do 1 minus the probability of z less than 1.8375 to work from the left. And so here on the table, we have 1.8375, so 1.83, it would be a value in between these two numbers. So you would do 1 minus that. But however, using the table won't give you the exact numbers. So what's preferred in this course is to use a calculator. So the table works great to get an estimate, but to get the exact number, I suggest using a calculator and using the norm CDF function. And so when you use the norm CDF function, you first input a lower bound, which in this case is like -infinity, but you can't actually put -infinity in the calculator. So it would be like -9 E999. So that would be the lower bound. And then if we're looking at this top line here, then the upper bound would be 120. And then we would have the mean, which is 105.3, and the standard deviation of 8. So that gives you 0.033068. So you would do 1 minus this value here, and that gives you 0.033068. And the reason why you do 1 minus that value is because it works from left to right. So the area under the curve. So if I were to just kind of backtrack again and draw out the normal curve, that's what I like doing. Drawing pictures helps. So I would draw a normal curve or a bell-shaped curve to resemble the normal distribution. And so then here we have the mean. So it's centered around the mean of 105.3. And so we want to find this green, this area under the curve, this shaded area here in green. So here we're going to say that's 120. So we want to know what is that area under the curve. So if we didn't do 1 minus the norm CDF and we just did norm CDF, that's going to give us this white part under the curve. But we're interested in this part. So that's why we would have to do 1 minus this area to get this area, because the total area under the curve is 1. So that's one way to do it. Or you can also use the standard normal distribution, which has a mean of 0 and standard deviation of 1. But in order to do that, you would have to use your z-score. So the bottom line is using the z-score. So where the z-score here for x being 120 was 1.8375. So that'll be the upper bound here. That'll be this value. And then the mean of 0 and standard deviation of 1, because it's a standard normal if you're using the standard, if you're using the z-score. And so you'll get the same answer. I recommend doing this first method here, where I'm not converting into a z-score first if I'm not being asked to. Just because it's less chances for error, it's less computation, and you can just put it into the calculator. However, sometimes you may be asked, which we'll see in the next task, about using a standard normal. So it's good to know how to do both. Okay, so that's part A. Next is part B. So we want to find the probability that x lies between 100 and 110. So here, if I were to start off drawing the normal distribution, we have our mean of 105.3. And so, so this value here is 105. So 100 is somewhere below that, and 110 is somewhere above that. So I'll just draw that in. And so we want to find the area under the curve that's shaded here. So we can use the norm CDF function. And here our lower bound, instead of it being infinity all the way out here, our lower bound is 100 and our upper bound is 110. And then our mean is 105.3. That hasn't changed, and the standard deviation is 8. So when you put that in your calculator, you get 0.467741. And last but not least, find the value alpha for which the probability of x less than alpha equals 0.25. So here, we're given the area under the curve, and we want to find at what value this alpha is. So instead of doing norm CDF, we're going to do inverse norm. And so that it works from left to right as well. So because here, oops, sorry, the probability that x is less than alpha, so that's this area under the curve. So that would be 0.25 is that area. And then the next value that you put in your calculator is the mean. So that's still 105.3 and the standard deviation of 8, and you'll get 99.9041. So to just kind of show you when you put things in the calculator, the professor has already gone through the steps of how to do it, but just to kind of show you, if you were to, so this first example here, norm CDF, if this only has 3 values, I forgot, like I didn't put the lower bound here, so I should have imputed 4 values, but there's only 3, so it gave me an error. So when you do it correctly, and this is for part A, you'll see that, let me go back to just show you what I'm doing. So for part A, I'll just show you that these two are equivalent and what it looks like in the calculator for this line up here and then this line down here. So anyways, so here you put the lower bound, and it's kind of hard to see my cursor, but the lower bound is like negative infinity or -9 E999. And then we have the upper bound, which is 120. And then we have the mean 105.3 and then the standard deviation 8. Or you could do the same thing with the z-score. So with the z, with the standard normal distribution, we have that value, our z-score here, and then the mean of 0 and standard deviation of 1. And you can see that you'll get the same answer. So do what makes sense to you. Okay, so that completes task 1. So now we're on to task 2. So task 2, we want to find a value of the standard normal random variable z, call it z0 such that, and then we have these two prompts here. So for part A, we want to find the probability that z lies between negative z naught and z naught, and that equals 0.8472. Okay, so just to refresh our memory here, just standard normal distribution, mean 0, standard deviation 1, so it's centered around 0. So my first step, I always draw a picture. So I'm going to draw the standard normal distribution. I'm going to write in what my mean is, which in this case it's 0. And then here I have values negative z0, and then positive z0 or z naught. And we're given that this probability, so the area under the curve from negative z sub 0 to z sub 0 is 0.8472. So that's this area under the curve in green. Now I want to find, in order for me to use the inverse norm function to get this value, I need to know what this area under the curve is to the left, because it works from left to right. So initially I wouldn't, I'll go over how to find these values, but when I'm first just writing the information, I only know what's sandwiched in between these two green lines here, which is negative z naught and z naught. So my next step is to find what is this area under the curve here. So I know that the total area under the curve equals 1. So I'm going to do 1 minus this value here, and that'll give us the remaining area under the curve. So that's 0.1528, but then I need to divide that by 2 so I can get the area under the curve to the left, and then the area under the curve to the right of the C0. So when I divide it by 2, I get 0.0764. So because the normal distribution is symmetric, I'm going to get a negative 0.064 to the left of negative z0, and then I'm going to get a 0.0764 to the right of this positive z0. Okay, so now I'm set up to be able to use the inverse norm function because I know the area under the curve where the different dividers are. Okay, so there's 2 ways that you can think about doing this. So here, the first way I'll show you is we can use the inverse norm function to find this value here, which is negative z0. And so negative z0 equals the inverse norm of, so here we would have the area under the curve from the left, going from the left to the right. So that would be starting in negative, so it would be starting all the way out here to negative z0. So that's negative, or sorry, that's 0.0764. So that's that area under the curve. And then because it's standard normal, our mean is 0 and our standard deviation is 1. And we get this negative value here. But the question prompted us, and if I go back, we want to find what our z0 is. So we found what negative z0 is. So in order to find z0, we would divide by 1 or negative 1. and then that would give us our Z0. So our answer is 1.42971. So that's one way to do it. It's kind of 2 steps, but it's simpler in the way of you only use this value here. So from the area under the curve from like negative infinity to negative Z0. Okay, the second option is you can use this value here. If we want to find this Z0, then you don't have to remember to divide by -1. And so here you would have to add, we would want the area under the curve up to this point. So we would have to do 0.0764 and add that to the green area 0.8472. So the area from negative infinity all the way up to here. And then our mean is still 0 and our standard deviation is 1. And that will give us 1.42971. So here you'll notice that's positive. So the absolute value of this equals this because it's symmetric, but that's 2 ways to do it. You just have to remember, like on an exam, you would want to, the sign does matter. So it's asking what Z0 is. Okay. Next is part B. So we're still on a standard normal, but here we want to find the probability of Z less than or equal to Z0. And that equals to 0.209. So here, if I'm going to just draw the information that I'm given, I'm going to first draw my curve and then center it around my mean, which is 0. And then I'm going to put a Z0 somewhere on the line. And I'm given that the area from the left to here, because it's less than or equal to this value, is 0.209. And so now I can use the inverse norm function on my calculator. And so the area under the curve is 0.209, and then the mean is 0, and the standard deviation is 1, and that gives us negative 0.809896. Okay, so that's sums up task 2. Now we're on to task 3. Timber beams are widely used in home construction. When the load, measured in pounds per unit length, has a constant value over part of a beam, the load is said to be uniformly distributed over that part of the beam. Uniformly distributed beam loads were used to derive the stiffness distribution of the beam in the American Institute of Aeronautics and Astronautics Journal. Consider the cantilever beam with a uniformly distributed load between 100 and 115 pounds per linear foot. Okay, and then we have these prompts. So the main thing to get from here is we have a uniformly distributed random variable, and we have that the load, the beam, the load is between 100 and 115 pounds per linear foot. So here our A for our uniform distribution is 100 and our B is 115. Those are the main takeaways from this prompt. And so here I have on a separate task or a separate slide, the 3 prompts. So the first prompt is, what is the probability that a beam load exceeds 110 pounds per linear foot? So here we want to know the probability that X is greater than 110. So before I get into these, if just to kind of give you a recap, so a PDF of a uniform distribution. So if a uniform follows AB, it'll look something like this, where the function here from 100 to 115, or from A to B, is 1 over B minus A, or in this case, 1 over 115 minus 100. Okay, so going back to part A. So what is the probability that a beam load exceeds 110 pounds per linear foot? So we want to know the probability that X is greater than 110. So here we would do 115 minus 110. divided by, here's our denominator, so 115 minus 100. This is our A and this is our B. So when you simplify that, you get 0.3 repeating. And then part B is, what is the probability that a beam load is less than 102 pounds per linear foot? So here we would have the probability that X is less than 102. So here we would have 102 minus 100, and then divide by that denominator of 115 minus 100. So when you simplify that, you get 0.133 repeating. And then last but not least, find a value L such that the probability that the beam load exceeds L is only 0.1. So here, the CDF of a uniform distribution is f of x equals x minus a over b minus a. So here we're asked, what is the probability that x is greater than L? And that equals 0.1. So we want to know what this L is. But because the distributions work from left to right, this equals the probability that x is less than L equals 1 minus this value here, which is 0.9. So once you do that, then we can use the CDF here. So the CDF f of L equals, so here we would have L minus our A, which is 100, and then divided by B minus A, which is 115 minus 100, and that equals to 0.9. And so now we have this equation here, and we just want to solve for what L is. So we can multiply 115 minus 100 on both sides, which is 15. So then that'll get rid of this denominator here. So we'll have L minus 100 equals 0.9 times 15. And then we can add 100 on each side. I'm just following order of operations. And then so L equals 0.9 times 15 plus 100. And so overall you get 113.5. Okay, now task 4, which is the last task. So the optimal scheduling of preventative maintenance tests of some but not all of n independently operating components was developed in reliability engineering and system safety. The time in hours between failures of a component was approximated by an exponential distribution with mean theta. Okay, so the main takeaway is that we have an exponential distribution and the mean is theta. So here we have 3 prompts. So I'm just going to go to the next slide because I copied them over. So just to refresh our memory, so the key takeaways, x follows exponential distribution and theta is our parameter. And then our CDF of an exponential distribution is that f of x equals 1 minus e to the negative x over theta. Okay, so part A. Suppose that theta equals 1,000 hours. Find the probability that the time between the component failures ranges between 1,200 and 1,500 hours. Okay, so we want to find the probability that x lies between 1,200 and 1,500. So that would be f of 1,500 minus f of 1,200. And this here is the cumulative distribution function, or CDF, which I wrote above. So here we're going to just plug and chug. So we have f of 1,500. So we're going to put 1,500 where x is. So we have 1 minus e to the negative 1,500 divided by our theta, which is 1,000. And then we're going to subtract that from f, the CDF of 1,200. So that would be 1 minus e to the negative. And now we have 1,200 as our x above. So that's 1,200 divided by, and then our theta is 1,000 still. So now once you put that in your calculator, you'll get 0.078064. Okay, So that's part A. Next is part B. Again, assume that theta equals 1,000 hours. Find the probability that the time between component values is at least 1,200 hours. So at least means that it's greater than or equal to. So we want the probability that x is greater than or equal to 1,200. So that's 1 minus, that's equivalent to 1 minus the probability that x is less than 1,200. So here, this is the complement of this. So we've covered in previous recitations that the probability of something equals 1 minus that its complement. So that's all I'm doing here. And the reason why I'm flipping it is because distributions work from left to right. So here, 1 minus the probability that x is less than 1,200 equals 1 minus the cumulative distribution function where f of 1,200. So here that's 1 minus, and then the distribution, or the cumulative distribution function is 1 minus e to the, and then here this is our x, so negative 1,200 divided by, and then this is our theta, so that's 1,000. So 1 minus our f of 1,200 equals 0.301194. Okay, so that's the probability that the time between component values is at least 1,200 hours. All right, now the last part. So given that the time between failures is at least 1,200 hours, what is the probability that the time between failures is less than 1,500 hours? So here we have language that is saying given that, and then something, what is the probability? So this is kind of a key word for conditional distribution, or a conditional probability. So here we have the probability of B given A. And so what is B and what is A? So here I'm going to say that the time between failures is at least 1,200 hours. That's going to be event A. And then event B is going to be that the time between failures is less than 1,500 hours. So here we want to find the probability of B, which is the time between failures is less than 1,500 hours, given A, which is the time between failures is less than, or is at least 1,200 hours. Okay, so the conditional probability equals the probability that A intersect B divided by the probability of A. So luckily, we already solved most of this problem because the probability of A intersect B, which is the probability that event A happens and event B happens, is given in part A. So the intersection here is, so the probability that the time between failures is at least 1,200 hours, and that the time between failures is less than 1,500. So that's here. That's the same thing as saying, what is the probability that the time between component failures ranges between 1,200 and 1,500? So that's part A. So we already found that, which is 0.07864. And then the probability of event A. So that's that the time between failures is at least 1,200 hours. So that we found in part B. So that's 0.0301194. And so when you take the answer from part A and divide that from the answer from part B, we get 0.259, which is the answer for C. And that concludes recitation 9.